welcome everyone to the call on behalf of the Victorian IHEA committee. We've got Kalpana, who's a Sustainability Solutions Consultant at Honeywell, presenting today. And she's going to be providing an overview of Long Bay Forensic Hospital and the solar PV work that Honeywell did out on that site. Kalpana comes to us with about 26 years experience in the building automation industry, working in a technical capacity across APAC, driving sustainability transformation through the Honeywell portfolio and in conjunction with Honeywell's customers. Working on project management, process deployment, detailed design engineering, sales, marketing, and offer management for Honeywell across the Honeywell portfolio there. So we'll be taking questions at the end, but feel free to put anything that comes up as Kalpana presents in the chat for this meeting as well. So with that, I guess apologies for the grey bits on the screen. We'll work through that throughout the webinar, but across to you now, Kalpana. Thank you.
Thank you, Michael, and good afternoon, everyone, for giving your time to this session. I don't see any grey bits at my end, so I'm going to talk as if you can see the whole screen. But if I say something and you're not able to place it on the screen, I apologize. Please put in your questions, and I'm happy to answer them at the end of the session. So we're going to talk about solar PV and EV charging station that we deployed at Long Bay Forensic Hospital in New South Wales. I'm based out of Sydney. And each of you may be at certain level of competence in this space. So I'm going to just talk about things on how we went about designing the solution, what parameters we considered, what was the before and after ratio, and what does that implementation look like, and really understanding what are the areas you could look at if you're into that area of expertise, you're on a learning journey, you already own a business, or you're using it for academic purposes, or you're designing your own for your own customer. So happy to take any other questions on larger scale projects for this situation. Let's get started with the agenda. So we're going to talk about what is this hospital about. It's a forensic hospital connected close to the correctional facilities in Maroubra. So the type of clientele that comes to the hospital are coming directly from the correctional facility. So they're normally patients which have got certain element of serious health and mental issues. So quite dynamic, unlike the typical hospitals that we see around. So really designing the solar PV system, the starting point was, okay, what roofs are safe to put it on? And as a first part of phase A, we started with the JHAC, their administration building, where none of the patients are allowed. And at the end of this deck, I will show you what the hospital also looks like. Initially, we had to really understand what the customer wanted and who were the players in this whole program. So there was Ausgrid, who was their energy provider or utility provider. There was the building itself. So it's a 137 beds hospital. And that's the customer who's paying the bill. And then there is the solar PV system or the solar PV supplier, which is totally environmental driven, really depending on the amount of sun that can generate enough amount of energy for the facility for the day. And then whoever gets the money is a happy person, right? And then there's Honeywell, who acts as a technology partner, where we were able to understand the customer requirement and design it in line with what works for the customer and in their benefit. Okay. So we got around creating this application. The customer is part of Justice Health, and they have very few EV charging station requirements because not many EVs drive up there to do a DC fast charge. But surprisingly, the facility did not have any solar panels on the roof when compared to a lot of other facilities you see today. Now, we designed a 100 kilowatt solar PV system for them, and we also installed 4 22 kilowatts AC EV charging stations and 1 DC fast charger. I want to talk more towards the 100 kilowatt solar PV system and how we went about that. So starting with the baseline, which is the beginning fundamentals of any energy program, followed by measurement and verification. The blue bit is really the current energy consumption for the customer. That's the baselining for 2 years that we conducted. And if we simply overlay the peak sun hours for that time period, then you get the idea of how much solar energy will be saved for that customer over that time period. So the yellow bit is really the savings potential, which gives you an instant idea that, yeah, this is very much doable. Customer can save more than 50 to 60% of their current energy consumption, because you can see there's quite a bit of sun to take care of it. So we did the maths, took their data, put in solar panels in our calculations, and we said, okay, you'll get an expected 15% energy savings reduction and an 11% on cost. Now, what we need to remember is that the kWh savings is not directly proportional to the dollar value saved, because there are several parameters that play a very important role in it. If you look at the kWh savings, it's really about the time of use, how the customer is using the energy consumption, what is the type of the facility, what does that 24 hours curve look like. And if you look at the dollar value, then it's really about how much the utility company is charging the customer based on the time of day. What are the other fixed charges involved with that? And that's the deep dive this session is about, to really understand costs. Solar PV systems are way more than putting in some solar panels on the roof, add an inverter, and let's get started. When you design larger systems, it's all about maximizing the yield, and it's all about looking into the right parameters that work for the customer and even understanding what kind of billing schedule they have. Again, part of the baseline, we said, hey, okay, if you're looking at the graph, the consecutive graphs, you will see the left side graph is the bar chart is slightly higher, and the right side bar chart for that month is slightly lower, which clearly shows that after doing a calculation, we said, hey, yes, you will get around a percentage of savings, which could range anywhere between 8 to up to 15% savings over the time of the year. Once again, we need to remember we've got 4 seasons, so that will also impact the amount of solar PV generated. And when we look at the kilowatt or megawatt hours, we saw a similar pattern, but again, it's not directly proportional. So the gray bit is really the current consumption of the facility, and after implementation, you see the colorful bit, which shows the reduced energy consumption in energy terms. Now, that's again a different percentage compared to the dollar value. What you will notice is the colors. So there is a different time of use where the customer is paying different prices based on the time of day they are consuming the energy. Now, let's get into the deployment. This is all about the baselining and understanding the customer's profile, how many beds, what is their utilization, what do we believe is going to be a good savings profile. Now, we talked about the players at the beginning, so we're going to start with Osgrid. So Osgrid is a utility provider, just like many other providers in the country. And if you just look at the heat map, it's very clear. Green is when they charge very low rates, time of use. So they charge around 10 cents per kilowatt hours. And that also depends on the arrangement the customer may have with the utility provider, which may also change annually. Okay. The orange bit is the shoulder rate, and the red one is the peak rate. But you also see that the utility provider is not really charging peak pricing during the autumn and the spring season. Okay, so the customer is really penalized for using high energy during the peak summers and peak winters, which is a necessity for the customer. And that was the biggest challenge, because the sun may not be shining at that time. So now understanding really the landscape of time of use and how to break this down and make sure that the solar panel production actually helps reduce the charges is where the complexity arises. So step number 1 is to really understand your energy provider and what does that heat map say and what kind of charges exist. And this is not all. Outside of this, the customer also pays for fixed meter charges. They pay for capacity charges, maximum demand charges, and other miscellaneous charges. So sometimes you would be surprised that the peak demand charges far supersede the time of usage charges on a monthly or daily basis. So that's another very important parameter to look into, and we'll see some of the solutions that we can come up with. After installing the solar panel, we came up with this curve, and this is for April. So this is as real as it gets, right? And you see the purple bit on the top left side where the sun is not shining because you're only going to get the sunshine in autumn for a fixed period of time during the day. So you can see around 7:30, the sun is rising. You're getting quite a bit of sun, but there's a little light blue. And then you're getting a good amount of sun. And then around 5, the sun is setting. So really capitalizing on that curve. But then you also see some purple circles in that graph, which I have shown in the bottom right corner of the screen, which clearly shows the clouds or the days when there was no sunshine directly on the panel. So there might be sun elsewhere, but cloud cover is a very, very common problem where you might not be able to extract maximum yield from the solar panels. There are several softwares in the market that can be used. One of them is Helioscope, that can be utilized to actually understand the yield, the orientation, and the direction of the solar panel, and how the solar panels should be connected to the requested inverter. And then you should be able to calculate the solar PV generation. But what we noticed is that the peak sun hours were generated for a short window of time, and we tried to understand, okay, how does this benefit the customer? I'm not getting into the design details of Helioscope. That's a training exercise in itself, and it's pretty straightforward. There are a lot of other softwares that do exactly the same thing. This is really about understanding the customer's requirement and matching it with your solution. And then we look into the peak sun hours. Now, this information can be made readily available from the BOM website. So you will get real-time data on how many hours did the sun really shine. For people who are new to this space, and for the veterans, it might feel a bit repetitive, but the fundamental to really understanding how the solar panels perform is how you lay your solar panels in what direction. In this case, the solar panels were laid flush mount. So if that's how the solar panel is laid and the sun rises from the east, you get a certain amount of solar irradiation, that is watt per hour, over a period of time, and then at 12 o'clock you get maximum sunlight, and then it reduces. But you'll see on a lot of roofs the solar panels are laid on the east-west direction, so you can benefit from the rising sun and the setting sun at the same time. Okay, so really depends on the roof structure. Now that becomes another very important parameter in understanding how much yield can I get. Just because I have solar panel roof space doesn't mean I can get all the yield available out there. What if your roofs are facing south and north? You would not be able to benefit from any solar panel solutions in those cases, or it would be a bare minimum unless you can find the mechanism to provide the tilt. Okay. So this aligned with the peak sun hours and the solar PV generated kWh for that whole month. So we said, okay, yep, that matches. The inverter is performing at its maximum efficiency. Now, once again, the inverters we know do perform at 98 to 99% efficiency, but a solar panel specifically only performs anywhere between 13 to 18%, although there are claims of up to 25%. Now, if you would ask why, the main reason being, one is solar panels are not going to be working 24/7 because there is no sun to perform it at its maximum efficiency 24/7. They only will work for specific hours of the day. And secondly, when they do work at specific hours of the day, they may not get the maximum amount of sunlight or irradiance to be able to provide its maximum output because of the moving direction of the sun. So some really basic fundamentals. So that's what we realized. So we had to consider all these base requirements before going into the calculations. When we came out the calculations, we realized there you go. For April, we did find a decent amount of savings in kilowatt hours, ranging between around, I can see the numbers here, between 9% and even up to 19% on certain days of the month, because there could be certain days where the solar irradiance is quite strong and that particular solar cell is performing at its maximum efficiency or maximum output. And certain days, even if their solar irradiance is strong, we'll have a cloud cover for a couple of hours suddenly, and irrespective of that, your solar PV system will not provide its maximum output. So these are the uncertain factors or unpredictable factors when you install a solar PV system. So we brought about these results, and you see the blue bit is still where the customer will continue to pay the price for their regular energy consumption. Now, you saw at the beginning, I showed you the time of use that came from Osgrid, and now the yellow and the green are where the time of use is split between 24 hours a day. What we've seen is the customer is paying a higher amount in the yellow zone, which is the shoulder area, and the green one is the off peak. If you look at the solar PV generation, it's really happening just after 5:30, and then it's kind of dying down after 4:30. So the customer is still subject to peak pricing, or they're paying very high prices around the 5 to 7 p.m. mark, purely because they are starting or switching off some operations around that time, and the same applies around 6 and 7 a.m. mark. Now, this is not the complete story, right? Okay, the solar PV system is working, it's doing its job, and it is providing savings over a 24-hour period for the customer for a specific amount of time. But can we do more? Can we just deploy this and provide even more savings from the solar PV system? What else can change? So another way of operating the system, so now we're literally like double benefiting from this solar PV installation. So we could either shift the load, what's happening between the 5 and 6, to the early morning hours around 6 to 7 p.m., or we could move the load later to the off-peak timings. So what we're doing is we're moving the higher energy demand load requirements, and that's again something you sit down with the customer, you discuss, hey, exactly what has been happening here. We realized that some of the HVAC equipments were actually shutting down or switching on because it is evening time, and this is a patient-based hospital, so there is always occupancy over here. So we were in the process of discussing, can some things be moved or delayed for later in the day? Now, this takes care of two very big things. One is the first graph, if you shift the load from the peak time to the morning time, you could utilize the free solar energy. So you're doing it for free without paying to the utility. And secondly, even if you're paying a lower charge, a lower price, cents per kilowatt hour, because you're consuming that energy when you are in your off-peak time period or time of use. The other one is to shift that again to later in the day or replace it with a small battery. And that's a possibility too. And I'll go into the pathways on how that can be achieved. So you can do multiple things over here just by introducing one solution. And this is only solving a small portion of their customer's energy requirement. We're still going to explore the whole facility. Sorry. So coming to the savings, what does the dollar value look like? And you will notice that throughout the month of April, just that 100 kilowatt solar panel was able to save energy around, I'm seeing the numbers here, anywhere between 9% and 20% on some days, because it's varying. And the variation is, again, a complex equation of multiple things, as we've seen. The dollar value is dictated by what time did I switch on the light or switch on the air con? When did my meter ramp up, or when did my pump ramp up? And was that at 2 o'clock in the afternoon or 2 o'clock in the morning? Was part of the time of use was that? What was my signed up maximum demand or capacity charge for that month, because that could also be a variable and that also changes sometimes with some very large customers. So that's another area you want to consider. So savings were pretty impressive in the first month itself. I've drawn that green line to show you the drop in the customer energy spend, which clearly demonstrates that, and this is only autumn, which is showing all these savings. So if you extrapolate it to the 12 months, then the savings would be a lot more impressive, getting higher savings from the summer season compared to the winter season. Although we need to remember, more the sun, more the energy production is not true. Hotter the panels, lower is the energy production. Solar panels perform best at its maximum efficiency in cooler climates. Okay. If we did that number 1 and number 2, which I showed you in the previous slide, then you can drop down your energy consumption even further without providing additional investments from the customer. So really a no-brainer, must do. And you can see now the ripple fold effect of just having that 100 kilowatt solar panel and how you can utilize that savings and move it around to capture additional savings. So what did the statistics look like? We committed around an 11.8% just for that month. You remember at the beginning I showed you the graphs with the before and after bar chart. So we said, hey, okay, we guesstimate based on your load profile and your energy consumption patterns, you'd get around 11.8% on savings for April. And we managed to deliver 14.2%. Similarly, on the dollar values, we said we gave it to you around 8.6%, and we managed to deliver 14.8. Now, you will again see that they are not directly proportional. The kWh and the dollar value have two very different variables on how they provide the savings, and hence the payback will also differ. Because payback is calculated in two ways. One will be your payback on your energy savings, and the other will be the payback on the dollar value invested. Okay, so what does this graph look like? Oh, sorry, what does the site look like? I mean, so this is a site. This is the Long Bay Forensic Hospital, and we implemented the solar PV system on the JHAC building, which you can see here. The next steps, which we are currently focusing on with the customer, are to populate the rest of the facility. Now, all these other bits over here are the inside the facility. If you see in the middle and the right side, that is the hospital itself, and outside of the boundary are the administration buildings. So that was a good test case for us to try out. But we've seen these fantastic results just with this small system here. So the ambition would be then to move on to future phases and eventually populate all of the solar panels on all the roofs to get maximum yield. Now, it would be exciting to see what that maximum yield would look like, and I have something interesting to show you. If you focus on the green bar on the screen, you will see we're drastically reducing the energy spend for the customer. And by the time we finish off with the entire program, the customer's energy consumption would have reduced by 87%. And their cost savings would have also reduced by 64%. Okay, so it's a no-brainer why solar PV panels are helpful to reduce your energy consumption, but it's more than just a combination of panels doing what they're supposed to do. If engineered correctly and considering all the factors that we have discussed right now, it really, really helps in extracting maximum yield for the customer. Now, it doesn't stop there, and I'm calling it the blue zone because a lot of people or a lot of customers don't move on to the most obvious next step. And that's when you put in your battery storage. Now, the battery storage can go at any phase, any time, and it could go at the beginning, or it could be with a combination, or it could go at the end. I've shown a small Honeywell Ionic battery over here. It's a small, around 225 kilowatt hours battery, just for pictorial purposes. But when we calculated, we said, hey, okay, we can bring down your energy spend a lot more if we put in a 120 kilowatt, 350 kilowatt hour battery. And you remember I showed you in that graph where you could shift some of the load to later in the evening, or you could discharge the battery around that time, peak time. How does that help? The big dollar savings really comes from going back to the utility provider and renegotiating the reduction in your capacity charges and your maximum peak demand. If the customer is not utilizing that kind of high curve of maximum peak demand, bringing down that maximum peak demand curve sends back thousands of hundreds of thousands of dollars back to the customer's pocket. And that's what utility companies would never want you to do. But by providing a proper technically engineered solution, you can demonstrate this to the customer and then sit with the customer and go and talk to the utility provider after a 12 months time period. I think they normally accept a 6 months to 12 months timeline to make sure that, yep, we're okay. It's making sense to us. We can renegotiate the peak demand and capacity charges. That's when the big money's flowing. Okay. So this is what it would look like at the end of the story, where the phase-wise approach is another deliberate approach I would consider, because each time when you design it, there are a couple of criteria that have to be considered. How far is the solar panels placed from the inverter? Do I need to run AC cables right up to the substation? Or can I reduce my cabling? There's a fair bit of detailed engineering that will have to be done upfront if you want to get this right every single time, especially when you do it in phases. If it's just one single roof, it's maybe a lot easier, but really understanding the concept of self-consumption, trying and driving every building and allowing it to self-consume based on the capacity or energy requirement of that facility would probably be a better engineered solution rather than looking at it as one large 600 kilowatt solar PV system. Okay, so quite a bit of engineering, value engineered options here to consider while designing your real life commercial scaled solar PV system. This would apply mostly for those kind of facilities where there are multiple blocks, building blocks, and you're trying to optimize the solar yield. Moving on, we have another 25 minutes. So I'm going to take another 5 to 10 minutes to go through the rest of the slides, and then I'm happy to take any questions that you may have posted in the chat. There's an extra element here now. We talked enough about the hardware and we talked about the engineering expertise. Let's talk about the software. How does software play a role over here? There are several softwares in the market that can provide demand load management. What I've done here is, obviously working for Honeywell, we have implemented something called as the Forge Energy Optimization Program, which provides 4 very key components. And before I get into that, I just wanted to reiterate that it's powered by Microsoft Azure and it runs on Google AI Analytics, which is a pretty powerful dashboard to help the customer make decisions on the go and look at real-time analytics. You don't need to have a separate building management system profile, a separate EV charging system profile, and a separate screen for monitoring your solar PV or even batteries. You can have everything in just one platform. So this is kind of my favorite slide. So really understanding the value stacking and how it's going to help the customer. When you put in EV charging stations, and now because what's going to happen is the moment you put your EV charging stations, and if they're going to be operated at maximum capacity, you don't want to increase the amount of energy consumed by the facility and increase the energy bill. So that's when your solar PV comes in play and they have to work together. And that's when the AI-based algorithms related to your EV charging station will kick in. There are quite a few strategies you can use around here. I'm just going to introduce you to 4 of them that can be utilized pretty easily. One of them being load shedding. Load shedding we do in different ways. It's an old age technique. And it's really about understanding, okay, do I need to allow the EVs to be charged or do I need to run my air conditioning at 2 p.m. in the afternoon? Or if it's 5 p.m. in the evening or 7 p.m. and most of the staff has gone home and the requirements is not that much, can I do my EV charging at that time, or can I even do it overnight? So that kind of AI-based automated decisions can be driven by the software algorithms. Then we can look at load shifting. Can I shift the load of charging during the sunshine hours rather than pre and post sunshine hours? That way, I will reduce the amount of load on my total energy requirement to try and maintain the maximum demand that I have signed up with the utility provider. So again, that's an algorithm based, and based on the characteristic behavior, you can design your program to function autonomously. You don't need somebody standing over there figuring out, okay, 5 EVs are charging, let's do load shifting. Don't need to do that, right? And then we've got load scheduling. When you do load scheduling, you can say, okay, I know that there are going to be X number of EVs charged. So these EV charging stations are going to be occupied between 9 a.m. and 4 p.m. So I'm going to allow for a schedule that is only going to allow 50% of the EVs to be charged on weekends and maybe 100% on weekdays, but I'm going to restrict the amount of time. And then the last one is load limiting. So that's the beauty of algorithms. We can actually reduce the amount of electrical energy or current that is actually sent to the EV charger. So it might take a little longer for the EV to charge, but if the person is going to be working there all day, then might as well utilize that extra power to run the building. So it's really a very complex and dynamic environment, especially when you have 20 or more EV charging stations. Now, in the future, we may plan to expand this to 20 to 30 EV chargers based on the fleet that's coming into the facility, whether the customer wants to add a revenue model to it and allow visitors and other people to charge their vehicles. And then that also changes the complexity and the dynamics completely. A lot of customers that I've seen have lots of solar panels on their roof, lots of EV charging stations. The building management system is working by itself and nobody's talking to each other. Everyone's doing their job. But the customer does not get the full benefit of all these technologies working together. The dollar savings or the dollar generation does not happen. Okay. This is a very small intro to how batteries look like. Now, this is not exactly how a Honeywell battery looks like. This is how every battery in the market looks like at a bare minimum. I've just provided some sizes over there to really give you a peek preview of what goes really into a battery storage system. And if you look at the different specifications of the topology, batteries come in different sizes, right from very small 250 kilowatt hours to 10 and 20 and even 200 megawatt hours. Okay, so this is my second last slide where I really want you to try and get the story together for the customer. When we're talking to the customer around renewable energy or optimization or energy saving, my first take is always, are we saving the energy for the customer? Are we making money for the customer? Are we doing both? And how does this fit in line with what the customer is really trying to achieve? Many times the customer may not know about certain ideas that are possible in their site until you explore and showcase it to them. And this was one of the classic examples which we were able to do for the customer. So really having that trust from the customer that you're going to actually help solve their problem is very, very important. We can do several things, right from reducing the demand side optimization, which we saw on the EV manager side, and I talked about those algorithms, by bringing in optimization or renewable so you can decarbonize it, and then you can talk about optimization of your greenhouse gas emissions as well by all those techniques, which are software driven mostly. Now, I have kept some extra time for questions. So this is my last slide to really show how the whole thing comes together and really getting, it's really like you can see the money man it was grid first and now it's the customer. So it depends on whoever is able to save money or spend money is benefiting from the whole story. And this is the job of technical consultant and engineering firm to really try and understand the storyline of what is the problem we're trying to solve for the customer, and really understanding their parameters rather than going with a blanket formula.